Episode 112, Unexpected JUMBOs. And welcome back to another edition of the Syzygy Podcast, episode 112, which, as Emily has just pointed out to me, is the beginning of the Fibonacci sequence. Hey, who knew? My name is Chris Stewart. I am sitting at the table in the office of the aforementioned Emily Brunsden. Emily, how you doing?
Hello. I'm well, thank you.
Good. Fibonacci sequence, one of your favourite sequences?
It is, actually.
In all of mathematics?
Well, only because I use it to go to sleep when I really, really can't go to sleep.
Sorry, how does that work?
Well, I just try and think of the numbers in order and just keep going, until I get so bored of doing it.
Does it work?
It does, actually.
Have you compared this to other getting to sleep mental exercises?
I haven't tried any other number sequences yet, so that could be something to try.
Interesting. Listen, listeners, if you've tried that and if it works, or if you haven't tried it and you try it this time and it does work, let us know. Be really interested to find out. But that's not what we're here to talk about today. We're not here to talk about Fibonacci numbers and getting to sleep. We're here to talk about something which has been in the news. This is one of those episodes which was triggered by a news article. I can't remember which one of us found it. Did I send it to you? Or did
you're the one on this one.
I sent it to you. And it was from the Guardian newspaper. Make of that what you will. Judge me or not by my media taste. But it was in the Guardian and it was in all sorts of other newspapers and on the radio. I'm pretty sure I heard it on the BBC. Like, it's just everywhere over the last week or so, which is about JUMBOs, not the big aeroplanes famous from the 1970s, but JUMBOs, which are planets. Emily, what's going on in the world? Why are we interested in JUMBOs all of a sudden? What's happening?
Well, here at Syzygy, we love a new astronomical term that's just been invented for not really any good reason.
And I didn't actually, I could have guessed immediately, but I didn't immediately assume this is an acronym. But of course, it's an acronym. So what's a JUMBO then?
So a JUMBO is a Jupiter, you got to count the U, mass binary object.
A Jupiter mass binary object. Okay, so Jupiter, I can imagine a planet, Jupiter, something of Jupiter's mass. So we're talking about basically Jupiter-y planets. Great, but binary objects?
Yeah.
Are we just talking about Jupiter-sized planets that come in pairs, or is there more to it? Like, what's the context here? What are we talking about?
That's pretty much what you were talking about. The interesting thing is that these have been discovered in the Orion Nebula. So this is a piece of research that's directly resulting from some awesome JWST images.
Right. So we're starting to see the benefits of JWSTs.
Yeah. So there's some kind of nice links here.
Not that long ago, and we were wondering, are we going to see some good stuff? Yes, we are. Yep.
So James Webb, Orion Nebula, really pretty, awesome.
One of the better nebulas.
Oh, yeah. And and the finding is that we've got these, call them JUMBOs or not, call them these planet kind of sized objects that are found in binary pairs. And the reason why this is interesting is because we don't really understand why they should be there.
Right.
By all accounts, they shouldn't exist.
Okay. All right. So we've got a few things that we need to unpack here. First and foremost, who has done this and where? Where have we, other than in the mainstream media, where are we seeing this?
Yeah. So no thanks to the Guardian article. I did dig up the actual papers.
Journalists and editors, take a good hard look at yourself. At the very least, tell us who wrote the paper and where we can find it.
Yes.
Right?
Yes.
This is science.
Yeah,
it's important.
Yeah. So this is a paper that's been submitted to... Well, actually, there's two papers here that have been submitted to journals on the 2nd and 5th of October.
Okay. So this hasn't been completely through the journalistic peer review process.
No.
Okay.
So that's interesting in itself because we're reporting on what I'm imagining is stems from a press release from the authors or the institution that the authors are in. They've submitted the papers. They must be pretty confident that these are going to get peer review.
Yeah, but it's interesting. More and more stuff is being picked up by the media through like preprint service and stuff like that as well these days. And I think it was during the pandemic years when there was so much pandemic-related research that, the media in the world was so hungry to know what is going on that journalists discovered preprint servers, which for anyone who doesn't know, scientists for years have been putting up what are called preprints before they've been accepted and put through the normal journalistic process. They will also throw them up for their peers, for other people, in their broader collegiate circle to read online saying, look, this one hasn't been completely finalized yet, but here's the the late stage draft, and that's a preprint server. And all the journalists discovered this and went, oh my God, here's a great treasure trove of research, which was great during the pandemic, except that it meant that an enormous amount of research which hadn't actually been peer reviewed suddenly was all over the press. Anyway, maybe it's from there, maybe it's from a press release, who knows? Regardless.
Yeah. So this is coming from, I picked up the papers off Archive. So the reason why these preprint servers exist, like, as you say, they're actually getting an article published in a journal takes months.
Yep.
It takes months to go through the peer review process, then the editing process, and then just finishing it up and putting it up online. It can take
takes time.
At least 3 months.
Takes time and money, increasingly.
3 to 6 months, indeed. And historically, at least, those journals then once published are often behind paywalls. So whilst if you're an academic institution, you're likely to have access, the general public don't. Mm-hmm. There's a lot of ongoing discussion about the use of public money for funding and how making open access is really important. So that is actually a changing scene, and actually much more research is open access than it ever has been before.
It could also, I wonder if it's also we're getting way off topic. We are coming back, I promise, listeners, we are. But it could also be a factor of something like JWST, which is now spitting out enormous quantities of data, and people are just falling onto it, going, just let me at it, let me do stuff. The sheer quantity of stuff that is coming out must mean that there are, new interesting studies just hitting the preprint servers a couple of times a minute. Just this constant stream of interesting stuff.
Yeah, well, that's also the thing. You want to say, well, hey, I've got this paper submitted, so you don't waste someone else's time who then starts a project on that, right, in the meantime.
Yeah. Anyway. So what are we talking about?
So 2 papers submitted. So they're by MJ McCaughrean. I'm going to probably not say that quite correctly, and SG Pearson. So there's 2 papers. One of them is a kind of big overview, global view of the study that they're undertaking. So these are scientists from ESA, the European Space Agency. Mm-hmm. They got these images taken by JWST late last year of particular regions of the Orion Nebula. It's about 37 hours worth of JWST time, just gathering the images.
That's a non-trivial amount of time.
No, it's a lot of time,
on a bloody great space telescope.
Yeah, and so it's one paper is all about kind of the design of the project, what the instrumentation and the setup of the different filters and how they set it all up, and then sort of a kind of tidbits of what the key findings are.
Okay.
Which include these JUMBOs as one of the key first discoveries. But actually they were looking at a lot more. They were looking at also circumstellar disks around. So this is where we need to bring in the context of the Orion Nebula, actually, because so the Orion Nebula is this huge star-forming region.
It's the closest one we've got, isn't it, to the Earth?
We understand it's probably one of the biggest in the galaxy as well.
Right, and just happens to be next door.
Yeah,
next door in the galactic sense of being. What did I read in the Guardian article? It's like 1,000 light years.
1,300 light years away. Yeah. Which is it's nice. That's a nice distance. It's close enough to study really well. Far enough that if these young stars sort of go supernova and things like that, we're not
in
bothered.
trouble. We're okay.
Yeah.
It is interesting that I've now been doing this podcast long enough that 1,300 light years now seems to me to be actually quite close. I think that's progress for me. I think I'm doing well. I'm starting to warm up to numbers.
Yeah, so studying the Orion Nebula, so they're looking for other things, as I say, circumstellar disks. These are disks around stars as they're forming. Really interesting. So lots of young stars that are in the process of being born.
Right, and the disks are where the planets get formed.
Yep.
So in a newly formed solar system, you've got all this other stuff swirling around the star that is forming out of the stuff. Mm-hmm. And the other stuff, the disk, goes on to form planets and other bits and pieces.
Yeah.
So it's a study. The broader study is let's have a look at this star-forming region just over there, only 1,300 light years away.
Yep.
And take a really good hard look at it. In order to understand better how these processes work.
Yeah, we've got these young stars with their circumstellar disks. We've got the JUMBOs. They're also looking at jets from young stars. So as they sort of collapse down, they produce these big jets of energy that are coming out. So in these outflows, it's sort of a knock-on effect of those as well.
Right.
So I just wanted to kind of give you the context is that this is a bigger study and this is kind of one specific outcome from that bigger study.
So that's interesting. We'll get back into the JUMBOs again in a second. But that was the bit that really got picked up by the press was JUMBOs, these Jupiter-sized binary things, whatever the hell they are. In the papers themselves, are they emphasized, or do you get the sense that that's something that either the press release people, the media officers at the institution, at the ESA, or the editors at the newspaper pointed at and went, that'll sell? Like, we'll get a headline out of that one. Like, how emphasized are they in the actual research?
Well, they are a bit because, as I say, there's a second paper which actually just talks about the JUMBOs. Okay, so you kind of got the overarching, this is setting up the whole project paper, which talks about all these different things. And probably deliberately, the first paper that's kind of following on from that are these JUMBOs. Because they are the most likely to hit the media because planets, everyone loves a good and everyone loves a good new acronym.
Exactly, especially one which is sort of, elephant related. So on that, then let's talk JUMBOs, because this is not just Jupiter-sized planetty things, because we found those in huge quantities. Like this is not just we found some more Jupiter-sized exoplanets somewhere. This is something different. So why is this interesting? What have they actually seen? Okay,
so the first thing is that these JUMBOs, they're not really being called planets. They are free-floating planets, or you might call rogue planets.
Right. And we talked about those like way back in this podcast, didn't we?
Yeah, we've talked about microlensing and planets, free-floating planets.
I seem to remember we did an episode like really early on.
Yeah, wasn't it? Like one of our first episodes was finding lots of these things in another galaxy. Yeah. So these are free-floating or rogue planets. That means that they are not going around a star.
Okay.
They're just out there in the space between stars, chilling out.
Does that mean – I was about to say, does that mean that they're not strictly exoplanets? But, I mean, backing back from that a second, you're saying we're not even calling these planets.
Well, exoplanets, planets. Well, planets – this really gets very political very quickly.
Oh, God, no.
And I don't really want to go down this road too far into what constitutes the definitions. We have a very
we get into trouble doing
very highly defined definition from the International Astronomical Union on what is a planet in the solar system.
Right, good.
And that gives us 8 planets, and that's what kicked out Pluto.
Infamously, yes.
Yeah. We have from 2003 a sort of working definition of what is an exoplanet, but that definition does say that they should be going around a star or a stellar-like object.
So we seem to be settling on whatever a planet is, there is a central star or system, perhaps a binary, could be, but there is a central, like there's a star involved.
Yeah.
A planet goes around a star.
Yeah.
Okay, so if there's no star, what is it?
Well, that's the thing. I think this is where maybe there's a little bit of a distinction between different parts of the astronomical community, and I think people who actually work in exoplanets tend not to care too much about the definitions.
Yeah, whatever. Look, we all know what this thing is.
It looks like a planet.
Move on.
It smells like a planet.
Yeah.
It just doesn't have a star, but that's fine. It's
Walks
still a planet.
like a duck. It's a duck. Yeah.
Yeah.
Okay, we'll leave the nomenclature for someone else. So we have, if I'm interpreting you correctly, right, we found Jupiter-sized things, lumps of stuff.
Yep.
So presumably, or Jupiter mass, but presumably they're Jupiter-sized. I mean, we're talking gas giants.
Gas giants, definitely.
Things.
Yeah.
But the latter part of the JUMBO acronym is the BO, the binary object. And so binary implies 2. And if it's not going around a star, are we talking about these things coming in pairs? Like,
that's right.
What's the deal here?
Yeah. So instead of having a star to go around, they're in some kind of gravitational orbit around each other. And it's all in itself, all those sort of things are kind of okay. That's all kind of allowed, if you like, by our understanding of physics, astrophysics, and so on.
There's no reason why that couldn't happen.
No.
Sure.
Until you get to the numbers.
Right.
Because if you just found 2 free-floating planets or happen to be orbiting each other, that's kind of statistically possible.
That'd be a sort of, kind of moment.
Because if we roll back to our ideas of how these planets sort of come about, for the Jupiter-sized planets, the real formation mechanism that we have is that they originally form around a star and then through some unlucky event get kicked out of their stellar system.
Right. Maybe something else really big wings on past and the gravitational interaction there just says, no, you can't be in this orbit anymore. You've got to go. And off it goes flinging across space. And sure, we can see that.
Yeah. I mean, statistically, that will happen. There's a lot of stars and there's a lot of planets. So it's going to happen to a few.
Yeah. And so finding one, maybe a couple, wouldn't be so surprising. It'd be a sort of, look at that kind of moment. But this isn't that.
No. And especially when it comes to the binaries, because it's not. And these are wide binaries. So they're not little tight binaries where the two planets are really like quite close together, snuggled in. They're quite far apart.
All right. Okay.
So the gravitational attraction between the two of them is fairly low.
Right.
So they're loosely held. If they were very, very close, they'd be very tightly held in that system. But they're much more loose. So to give you a sense of scale, we're talking about Jupiter-sized things, and the distances between them are kind of around about 100 astronomical units.
Okay, astronomical unit distance between us and the sun. What's the distance? Like, how many astronomical units is Jupiter from the sun?
So it's about 5.
5. So 100.
Well, yeah. So Pluto's about 30.
Oh, okay. Right.
Yeah. So
we're talking
35.
That's a really long way.
Yeah. So about 3 times the solar system.
That's amazing that can happen at all. But then I guess if they're sort of out there floating free across space, well, not floating, but, heading out across space, if there's nothing else nearby to upset that, then that really weak long-distance gravity, that's fine. That can still happen.
Yeah. So
if
you were, 2 planets were formed in some respective solar system, if they were formed in the same one and kicked out, it wouldn't really be possible for the binary to survive.
The odds of that would be pretty small.
Yeah. There's too much other gravity interplay in there. So they wouldn't have formed as this binary in a solar system and then got kicked out together. They would have had to been formed probably in different systems and then come together at some point for some reason.
What just sort of flung out across space and then happened to come near enough to each other at the right kind of speeds to go, let's glom on together and make a little binary system, which again just seems ludicrously improbable. So how many of these things are we seeing?
Well,
because presumably that's the point, right? Is that you wouldn't have a study unless you'd seen like more than a couple.
So in all randomness in this sort of system, so that we're in this cluster, we're looking at, so in the Orion Nebula, this is a study that's focused for the JUMBOs. It's particularly focused on the trapezium cluster, which is right in the center. It's a very, very favorite target for, showing off to the public with your telescope. The trapezium clusters, it's 4 bright stars in the shape of a trapezium.
Right.
But then there's a bigger cluster of stars that are around that. I think there's about 2,000 stars that form the cluster. And so in that sort of space, and if you do the sums of just randomly how many of these would you expect to find, you might get, if you're really lucky, up to about 3 binary systems. That's
on the assumption of we assume this many planets are being flung around, and so that's how many we would expect to get. And how many do we
about 40.
40.
Yeah.
That's significantly more. Yeah. That suggests that there's, something's wrong with our assumptions here. I was about to suggest there's a mechanism here, but that probably sounds a little bit too clockwork. But something's wrong with our assumptions.
Yes.
So do we have any sense of why, how, where are these things coming from?
Yeah, well, it's interesting. So you've got about 40 binaries and actually 2 triples.
Wow.
Yeah.
Wow. So these JUMBOs, these Jupiter-sized, not planets, Jupiter-sized planets, like they're forming their own little systems here.
Yeah.
That's wild.
It's quite cute, isn't it?
Yeah.
Obviously that means that the formation theories that we have of how this is what we call bottom up, where the planets are formed with the star. So they start off as something quite small. So our formation theory for Jupiter itself is that we had this sort of, as the outer edges of the solar system in the disk of the sun as it was forming, as that got cold, you sort of got a lot of freezing of material. So these kind of ice balls started to form. And then those sort of gathered up a lot of gas. So Jupiter's a lot of hydrogen, quite a bit of helium as well, atmosphere. So it just sort of scooped up all this gas.
Right.
So it grew effectively.
Kind of literally snowballs.
Yeah.
Like it gets a bit bigger, and then the bigger it gets, the more it just starts hoovering up all the stuff around it.
So that's bottom-up formation.
Yep.
Now, you could sort of look at it from the other way round and say, well, couldn't, as part of the collapsing molecular cloud, so this massive cloud of gas and dust that collapsed to form the sun or forms stars, we tend to form several stars at the same time. Couldn't it just have had little pockets of that formed smaller bits?
Kind of what I imagine in my mind's eye. Like I've got this image of sort of this big in my head. It glows, but whatever. This big sort of nebulary space, and then bits of it sort of down, and there's a star. But I could imagine something on the size of a Jupiter also just sort of down, and it's not quite big enough, but it's there.
Yeah, so this is where we can look at, I guess, some of the definitions. So when to form a star, to call it a star, really, it needs to be at least 80. I'm going to work now in Jupiter masses because we're talking in Jupiter masses.
Sure.
So to form a star, you need to have a molecular cloud that collapses down and forms something that's 80 Jupiter masses or more.
Right. And why that number? What happens at that number?
Because that's the number that you need that much mass so that there's enough gravitational crush to fuse hydrogen.
Right. You need that amount of stuff coming together under gravity so that the pressures and the temperatures down in the core get high enough to actually turn on those nuclear reactions, that energy, powerhouse at the core. Right.
You reach ignition for hydrogen.
Anything less than that and it doesn't turn on.
It doesn't turn on, or it doesn't turn on into hydrogen to helium fusion.
Okay.
However, if you've somewhere between 13 Jupiter masses and 80 Jupiter masses,
it's quite a big range.
You'll still get that gravitational tug. You still fall down, and during that collapse period, there's still quite a lot of heating that goes on. Right, a lot of friction, a lot of heating as the gravitational potential energy is released. And so these things can get quite warm, which means that they can glow. But they also get to a temperature where there's a little bit of deuterium fusion.
Okay. So they can it's like the engine's just almost turning over. It's almost starting. You're getting these little flares and a bit of heat, a bit of light coming off because of the sheer quantity of heat. But it's not self-sustaining. It's not going to keep going.
No, it's only for sort of a short period of time you get this deuterium fusion.
What do we call, are those brown dwarfs?
Those are brown dwarfs, okay. Yeah. So whether a brown dwarf, I mean, you might hear them called failed stars.
Right.
Which is a bit mean.
Bit derogatory. Like, come on, they're trying their best.
Yeah. But then anything less than 13 Jupiter masses doesn't really have a lot of gravitational force, or doesn't have enough to significantly heat the planet, object, whatever we call it. Actually, the technical definition of them tends to be PMOs, or planetary mass object. Yeah.
So, sorry, anything less than 13 is a planetary mass object.
Yeah. So, because I guess technically it's not really a planet unless it's going around a star. So it's a planetary mass object.
Can we just call it a planet? But okay, sure. Wouldn't it be convenient if we could just draw a line there and say that bit, that's a star, or a brown dwarf failed star. Let's not be too derogatory. And then other side of this line, planet. Like, wouldn't that be easy?
Yeah, but there's
but those planets, they're going around stars. But we've got these other planets, but they're still planets because that would be.
Yeah, I mean, some of these definitions are very loose. We don't know exactly what that mass is to be a brown dwarf or planet, for example. It's theoretical, but
I mean, even something which is 12 Jupiter masses as it's collapsing down, there's still going to be a lot of heat there. And you're going to you can see anything at a temperature. It's still giving off radiation energy. So where do you draw that?
Exactly.
Is it in terms of how much nuclear stuff does? Oh, who knows? Okay. All right, fine. Yeah. We'll leave that definitional thing aside.
There's probably a reason why these definitions have not been nailed down.
Fine. Okay. I don't want to be in charge anymore.
Yeah. So now, then if we go back to our models about molecular clouds collapsing, then this process is called fragmentation. So you can imagine little clumps of the cloud are fragmenting and collapsing down to form stars, to form planetary systems, etc. The smallest clump that can kind of actually collapse under its own self-gravity is kind of around about 7 times the mass of Jupiter.
Okay. All right.
So that's the smallest possible, I guess, planet, if you want to call it that could form from this top down.
Right, from the collapsing down of the cloud. Anything less than that, it just doesn't happen.
It just can't come together under its own self-gravity. There's too much other momentum of the particles and the thermal pressures and
other
so on.
processes get in the way. That it might try, but it'll fail. Yeah. It'll sort of things will waft away.
You can sort of draw up the perfect scenario if you want to, a very maybe highly contrived situation, which would get you the smallest possible clump of mass that could maybe sort of hold itself together in this way.
I mean, look, under very, very basic principles, you could take a completely still gas cloud and seed it with a little thing in the middle and it would collapse down. But that's if there's nothing else happening and it's not too hot. And so yeah. Okay.
So the very kind of best case scenario, if you tweak your models quite extremely, I think is you can get down to maybe 2.6 Jupiter masses.
Right. And that's being really, really, really careful and taking everything else away. And so you're not going to get something which is sort of Jupiter sized.
No. From
the top down, collapsing down of the cloud.
No. And to come back to this study, they actually found 540 Jupiter, well, let's call them PMOs, planetary mass objects, that were less than 13 Jupiter masses, so less than the brown dwarf dotted line. 168 of those were less than 5 times the mass of Jupiter. And actually there were a few of them that were less than that, and some went down all the way to 0.6 times the mass of Jupiter.
That's okay. Yep, that's getting down there. I mean, that's not anywhere down to sort of the rocky planets in our solar system. That's nowhere near the Earth, but it's still a lot smaller than Jupiter.
Yeah, and it's very problematic because remember that our minimum that we can get to is 2.6
through that process. Yeah.
Yeah. So as an overview, if you're looking, how do these planets form? Let's say you've got 2 that are about as mass of Jupiter in a binary system. They can't have possibly been formed in planetary systems because they wouldn't have, there's just no chance that they would have come together.
They wouldn't have been formed together. No.
Yeah. And so they couldn't have been formed together and then gotten kicked out because that's kind of gravitationally impossible.
Ridiculous. Yeah.
If they did form in different planetary systems and then come together, we wouldn't be seeing anywhere near the numbers of these.
Again, what are the odds? Yeah.
But equally, they can't have just formed out of the molecular cloud because they're too small.
Yeah. Weird. Huh. So do we have an answer to this conundrum? Or are we still at the stage of, hey, so there's a lot of these things. Any thoughts? Like anyone?
Well, no, exactly. This is exactly why the research is so important because and this is the finding that we're finding these things that are defying all our models of planetary formation, and we don't know what's going on.
I mean, that's the fun part, right? That's the best part of research is when you find the thing which is. I think we need to just go back and have a really good hard look at all of our assumptions and the things that we think we know about this stuff because we can't explain this. You know, it's not that often that you get something really new under the sun. And this seems to be kind of falling into that category of we really don't think there should be this many of these things in the universe. And there are lots of them. Yeah. So go and explain that. Yeah.
Which is exciting, right?
Yeah.
It's great.
Yeah.
So that's effectively why this has kind of come up through the I wouldn't say the noise, but through the everyday wonderful research that's coming out is because hang on a minute, this is really you can see why the astronomers are getting really excited about it. I mean, I did hear on pretty sure it was BBC Radio, there was an interview with one of the researchers and they were talking about it. And it just pointed out to me like how hard this stuff is to talk about out in the world, with people who are just doing morning radio, and they're trying to talk to a researcher about the latest thing in astronomy. And halfway through this, for a science story, it was a relatively long piece. And about halfway in, a couple of minutes in, the question was, now, sorry, these JUMBOs, are they in our solar system? And he's like, no, rewind. Let's start this again. Let's just
let's just start this again. Yeah. That was a bit revealing because people don't know this stuff.
Yeah.
Right? This is challenging stuff to even start talking about.
It's very easy for us to take for granted our just baseline understanding of how the universe works and just assume everyone has that.
Yeah. Oh, well, here we are. And people listening to this podcast, we're assuming that, you have an interest and probably a certain amount of knowledge above the norm for the world, but we still like to try to sort of break it down. So,
and if not, these are definitely not in our solar system.
Yes. So let's just be absolutely clear. These are not in our solar system. They are, in fact, about 1,300 light years away. Hey, one question I had about that when I was thinking about this earlier, like I said, I'm getting better, right? I'm getting better at figuring out, is that a long way away or is that a short? But if I imagine the Milky Way, right, which is a big sort of disky thing. Yeah, it's a galaxy which has got arms, like big octopusy galaxy type thing, right? This is in my head, okay? Just go with me.
I'm just giving you weird looks now.
Just go with me, okay? And I know that our solar system is sort of about 2/3 the way out along one of those arms. So what I don't really have a sense of is 1,300 light years away. Like, where is that in that picture? Like, is that basically in the same arm? Is it a completely different arm? Is it somewhere else entirely? How can I imagine if I was looking at the galaxy from say above? Any idea where we are?
Well, so if you imagine the galaxy as these spiral arms coming out, there's one of the biggest spiral arms is called Sagittarius arm. So it's this big, long, beautiful, curved sort of tentacle, if you like, coming out from the galaxy. I'm going with your octopus theme here.
Yes. This is going to catch on.
And then there is a little, what we call spur off the Sagittarius arm, which is us. So we're on the Orion spur.
In my analogy, that's a sucker. That's one of the suckers on the octopus's
Right, very good. Yep. Orion Nebula is also in that spur.
Okay, right. Yeah. So that's actually quite close.
Yeah.
Yeah. So it's literally just next door. Cool. Okay, that gives me a much better idea. Yeah. Excellent. Good.
So, interesting question. Let's try and segue this in a not totally awful way.
Good luck. Always like a good segue. Yep.
It's close, but it's far enough away that you could ask, how can you see these things and how do you know how big they are?
So, okay, two very, very good questions because we are still like quite a few light years away and seeing planets is hard enough when they're going around another star and you use that fact to actually see them, right? When you see them pass in front of the star and the star gets a little bit dimmer and a little bit brighter again, right?
Yeah, typically you need the star's light to determine there's a planet.
Yeah. If there's no star, how are you seeing these?
I'm glad you asked this question, Chris.
Yeah, nice one. Good segue.
Well, it's interesting. I mean, the Orion Nebula is actually close enough that we can resolve these objects as images.
As like you can actually see the thing itself.
You can actually see them. And I know that you can do your podcast magic and bring up an image that actually shows.
That magic has been done. Look at your podcast player of choice and you should see an image. Wow, that's awesome.
Yeah. So the interesting thing is you can say, well, why haven't these just been looked at? We've had big telescopes for ages.
Yeah, come on, astronomers.
Yeah, what have we been doing? Well, the Orion Nebula is a nebula, right? And the clue's in the title.
Yeah.
Nebula, nebulosity.
That's what it says on the tin.
Kind of this bright cloud, right? And so that bright cloud actually swamps the light from these kinds of objects.
Right.
So if you're looking in the optical, you can't see them because the rest of the nebula is just glowing so bright.
We're just looking straight into the headlights.
Yeah, exactly. Yeah. And these objects, although they're not causing any fusion processes and not producing any photons through nuclear reactions, they do have a temperature because from their formation, they have the residual temperature of just being objects, right? So their temperatures lie kind of around 900 to 2,500 Kelvin.
Right.
So, that's not so dissimilar if you want to put it in degrees Celsius. You can take off 200 and a bit if you want. Doesn't
make a lot of difference. Yeah.
But
in the high hundreds to the low thousands.
Yeah.
Yep.
So if you transform that temperature into what wavelength of light you need to look at those things in, because what happens, there's a relationship between temperature and wavelength of light.
Yeah, I mean, all things are glowing.
Yeah.
If you see something that is glowing red hot, you know that it's nice and hot. But before it even starts glowing red, it can still be hot. And if you look at that in the right way with the right kind of frequencies, then you can actually see it. That's what certain temperature scanning cameras and so on can do. You can go and get your house scanned to see where all the energy is leaking out and so on. And that would be in the infrared.
It is.
Wouldn't it?
Yeah, it's around 1 to 3 microns.
If only we had a honking great space telescope, which was really good in the infrared wavelengths.
And it turns out the nebulosity doesn't really glow that much in those wavelengths.
Okay.
It's much reduced.
So it's much more into the visible
Yeah.
and ultraviolet as well? Or
Actually, yes. Yeah, there's a lot of high energy processes going on in the nebula itself.
So wouldn't it be really handy if we had a honking great space telescope that was really good at infrared stuff? Do we have one of those?
Just the one.
Just the one.
Yeah.
Fortunately, it's a really good one.
So this is why this has taken James Webb. I mean, some of these objects have been known about for quite a while. So we must say this is not the first time we've seen these types. It's been known that they existed in the Orion Nebula at least around the 3 to 5 Jupiter mass area. That's been known since we had it's a revolution in its own right, the 8 to 10 meter telescopes come online. So that was all the early 2000s. We had things like Keck, Gemini, Subaru.
These are all these big telescopes up on the top of mountains.
Really big ground-based telescopes.
Are they looking in the optical?
Yep, mostly.
Okay.
Some of them can do some infrared, but the Earth's atmosphere gets in the way.
Right. So how are they seeing them then? Why wouldn't
they
have been
they're bright
blinded?
enough.
Okay.
So you've got big telescope. You can just get these. So the bigger the planet or the PMO, the brighter it is. So those 3 to 5 Jupiter mass ones were just bright enough to get with some of those instruments.
Right.
And then of course we had Hubble, and Hubble had a really good infrared upgrade in the late 2000s. 2000s,
right?
Do you know what I mean? The what do we call those? The
noughties.
The noughts. Oh,
yeah,
I don't like the noughties.
Okay, the noughts.
Yeah,
the ooze.
Yeah,
I used to like calling it the ooze because there's a
yeah.
Ooze.
Okay.
No, it's not going to go with me on that.
No.
Okay, I'll take
There's
the
a
octopus,
river,
but yeah,
not yeah.
Yeah, fair enough.
Anyway, yes. So in the late. So let's say 2009 to 2012, round about then, was when Hubble was looking at this region as well. So it had its upgrades to look really nicely in the infrared and did some
because Hubble
did
lots of stuff in the visible wavelengths, but also had the infrared.
Yeah, it had both an infrared and an ultraviolet upgrade later on in its life. Okay. This was really good. Yeah, so this is just kind of building on that, but obviously with James Webb being huge and
great space
very,
telescope,
very precise and in a lovely part of deep dark space at L2. It's just really getting to these really, really small PMOs now. So the ones that were less than 3 this is the first time we're seeing those in the Orion Nebula.
Which is the kind of thing that for so many years people were looking forward to JWST being up there so that we can have a really good hard look with this fantastic new huge telescope. At all of these things which have been tantalizing for a while. And seeing a few of these jumbo-ish things, although we didn't know they were jumbos because we hadn't seen the binary side of it yet. There's something to see there. Let's go and have a look. But I wonder how many astronomers could have predicted, you know what, this is going to completely turn on its head what you think you know about this stuff. And that's the coolest part about these big new missions is there's every chance that we actually really just don't get this stuff. And here's a classic example. We go and look at all of these planetary things and suddenly there's all this stuff we've got to figure out.
Yeah.
It's great.
Yeah. And these instruments don't just have they're not just bigger and therefore able to take in more light. We're able to observe in different and more precise ways. So James Webb has lots of really nice infrared filters. So a filter basically takes a little part of the spectrum of light and says we'll only allow these particular wavelengths of light through onto the camera.
Right, okay. So why is that important?
Well, this is really important because you can do kind of I'm going to introduce my own bias here. What I would call quick and dirty spectroscopy. So what you do is when you do spectroscopy, you take the light that you're getting and you split it up to all its constituent wavelengths and you see what's going on in each of those wavelengths. It's expensive for photons. So that means that you need a lot of photons coming in, really, really bright objects, so that when you smear them out over a lot of different wavelengths, you still get enough signal.
Right, because you've got to look at each of those different, the analogy being at each of the colors in the spectrum, you need enough red and orange and yellow and green and so on in order to be able to see what's happening at each of those colors, even though we're not looking in the visible, currently down in the infrared. But if you want to see what's happening in each of those little bands of wavelength, then you need enough photons in each of those wavelengths to do something interesting.
Exactly.
So you need a lot of light coming in.
So that's why we tend to only be able to do really good spectroscopy of really, really bright targets.
Makes
because
sense. Sure.
You just need the number of photons.
Yeah. Or you need a really, really, really big, good telescope with really good filters to carefully collect all of that light and then filter it.
Yeah, so the filters, you don't have to look at every single wavelength. You can say, well, these are the only the interesting little sections of the spectrum that I'm interested in. So I'm only going to get bits from those. And so you don't need as many photons in each filter. And you can do it without having a prism. You can do it without having all the really refined optics that you would have in, say, a medium to high resolution spectrograph. So you can do it in space.
Cool.
You can't do high resolution spectroscopy in space. That's the instruments, the instrument I use to do high resolution spectroscopy is about the size of this room.
Right.
And the precision optics, if you try and put that on a rocket, it's
not going to work.
It's not going to go.
It's not going to work. It's a non-starter.
Yeah, exactly. So, this filter is really, really important because then what you can do, because if you looked at, say, you've got your little blob that you've now found in the Orion Nebula, you say, okay, I want to know what mass that is. The way you do that is quite exciting, quite interesting. What you do is you take pictures of that object in lots of different filters. And if that object was a star, it would have a particular signature. If you sort of said, well, it's got this amount of photons in this filter, this amount of photons in this filter, this amount of photons in filter number 3. A star will have a very particular signature that's very smooth, actually. A star is what we call a black body. Well, it kind of behaves like a black body, or perfect temperature object. It's just that stars are wonderful.
Stars are lovely. We love stars.
They just have this lovely smooth curve. Planets, and particularly, these PMOs, they are cool enough that they have a much more jagged sort of profile if you take this.
Okay. So in other words, they're spitting out a lot more energy at certain wavelengths than in others. It's not a smooth curve from one to the next. It's sort of spiky.
It's spiky, yeah. Right. And it's spiky because in some filters, what you're seeing is on the atmosphere of these PMOs, there's things like water in the atmosphere, there's methane, and those things block the light. So you get this kind of massive drop in the amount of light you receive in those particular filters, and you get spikiness.
Right, okay.
And from modeling because all these objects are at the same distance, right? This is the wonderful thing about clusters. They're all the same distance away from us.
Yeah.
We know
to within a very small amount.
Yeah. So we know if that one's brighter than that one, it's because it's intrinsically brighter than that one, not that it's closer.
Right. Yeah. That makes sense.
That's great. So we can say, well, that one's quite bright and it's got the spikiness. Therefore, it's a PMO, but it's a high mass PMO because it's bright. Now, this one's got the spikiness, but it's really, really faint.
So
it must
it's
be
a low mass.
Yeah.
Right.
It's very clever.
It's very cool.
Yeah.
Very cool.
And so that's how you can pick out the masses of these things without having to go and do things like actually look at their orbital motions or other things that we would typically have to do for mass.
How do they figure out that they're binaries?
Now that's a very good question.
Like I can understand if they were really close and whipping around each other at high speed, but these aren't.
No.
These really aren't.
No.
So how the hell do you figure that out?
Well, again, this is actually quite cool. It's just proximity in the pictures.
Right.
Because again, this cluster is all kind of at the same distance. So there's not really much three-dimensional kind of information in this cluster. So you can't say that one's kind of half the distance to that one because they're all in the same place. So then you just look at how far they actually are away from each other. And again, you can say, well, if they were just randomly scattered, then you wouldn't see these pairings. But because you see so many pairings,
you might see a pairing because, I mean, as you say, they're all basically, it's like looking at a plane, right? Because they're all the same distance away. But actually, they're not. They're in a little three-dimensional ball out there, right? And you could see just by line of sight, one at the front of the ball and one at the back of the ball, and they seem to be right next to each other. And from our perspective, they are right next to each other. But from their perspective, they're not. They're way, way apart. But you'd be able to figure out, well, how often would we see that? And it wouldn't be terribly often.
No.
And so if you start seeing lots of these things turning up, you go, what's going on?
Yeah.
Either we're seeing a lot of coincidences or these things are actually in binary systems and they actually are close together.
Yeah.
Wow.
It's like if you scattered salt onto, your plate, you'd expect it to be more or less randomly distributed. But if then you saw that all the salt crystals, actually there's 2 of them in each of these places, you'd start to think, hang on a minute.
Something's happening here.
Yeah.
So we're not detecting that they're in binary systems from the way that they're moving, but from their proximity.
Yeah.
And inferring it's the only thing it can be.
Yeah. I mean, at best, 1 or 2 of these might be chance alignments.
Right.
But not 40.
Right. But you said they even found it like a triplet.
2 triplets.
2 triplets. So again, what are we going statistically there and saying the odds of that turning up just because of the way we're looking at them, very, very small.
Yeah.
We've seen 2 of them. So surely at least one of those is the real McCoy.
Yeah. There's not as much discussion about the triplets.
Right.
I guess there's more to be done on those systems. And indeed, actually, all these are candidate kind of JUMBOs, if you like, because this is just their first detection and they will need some confirmation. But the good news is that confirmation will be coming because the scientists have a proposal that's been going to go through to cycle 2 of James Webb.
Meaning what? As in the second phase of research?
The next observing
right.
round, which has actually started, I think, July this year. So it goes for another year. So it's cycle 2 we're into now. Where they're going to get some, I say spectra from, they're not what the kind of spectra that I do, they're very low resolution spectra, but they're enough to sort of confirm that instead of having just a few points to show over the different wavelengths of light, there'll be many more points to show that these things are actually truly planets or PMOs. So that's quite exciting too. There is a confirmation follow-up. So
where does this bring us then? Like, this is clearly captured the popular interest. It's been all over the press. Mm-hmm. It's a really interesting story for all the reasons that we've discussed, right? It's something pretty new and unexpected, and it's JWST, so everyone loves proving that was money well spent. But what are we getting out of this? What's the point?
Yeah, well, I think we've covered 2 of them, but I'm going to go into depth on a third.
Okay.
So I think we've covered the fact that let's say we don't have a very good definition of what a planet is.
Yeah, that's problematic.
We probably need to think a little bit more about that.
Someone should nail that down.
Yeah. We also clearly don't have a very good working set of models for the formation of some types of planets.
No, something's wrong there.
Well, because we can't explain these ones.
Yeah.
So that kind of needs a bit of attention.
Yep.
But actually, what I find very interesting about this is that we are pushing the limits of some of our observations of something called the IMF. Or the
International Monetary Fund. I know that one.
Yeah.
No?
No. The IMF in this case is the initial mass function.
Okay.
So when you have the initial mass function can be used in a variety of contexts. In this context, it's saying there was a molecular cloud and it collapsed down. Now, it might have formed so many things that were a few stars that were really, really huge. It might have formed quite a lot of stars that were kind of medium-sized, a few stars that were small, and maybe some of these teeny, teeny, tiny objects. But you can also consider the initial mass function as looking at just how many objects are there of each mass in, say, a galaxy.
Okay.
How many things do you have that are really, really huge, and how many things do you have that are really, really tiny? And you sort of plot a graph of size versus number of, right?
Sure.
You find that the peak ends up being sort of somewhere a little bit bigger than the sun, typically for stars. But there's this long tail, right, of really, really small objects. And so this kind of research is looking at actually saying, well, what is the number of things that are Jupiter-sized in a galaxy, for example? And that seems almost like research for research's sake.
Sure. I mean, it's a question one could ask.
But that tail matters because this whole function is how it goes in as a major input into how we understand how galaxies work.
Right.
Galaxies are mass, right? They're stars.
Galaxies are made of stuff.
Yeah. And so how you distribute that mass actually affects a whole lot of things about galaxies.
Well, I would imagine even as far as things like investigations of dark matter and stuff like that.
Yes.
Like, you really need to know where this stuff is.
You need to know the mass that you understand.
Yeah. You need to understand the mass you understand.
Yeah.
Yeah.
So that's not to say that these things are going to explain away dark matter. That's absolutely not going to happen.
Okay. That's we'll take that one off the table.
Yeah.
Okay.
But you need to be able to draw up a really strong model of your galaxy to see what the matter distribution is now, what it might have been in the past, and what it will be in the future, to actually evolve your galaxy through time.
So if you have a study like this which says, you know what, you really don't understand this chunk, which is a sizable chunk of the stuff in the galaxy. You don't get that. You should probably figure that one out before you start making assumptions about anything else to do with this galaxy. Yeah, that makes sense.
And the very, very early results from this are suggesting actually there's more of these very low mass or Jupiter mass objects than we would have expected, basically.
By like how much?
Well, the error bars are quite big, but
right.
Significantly more, maybe an order of magnitude. So maybe 10 times more.
Right. That's not mucking around then.
No.
That's not sort of, you're off by 10%. That's a lot.
Yes.
Yeah.
Yeah. And that therefore changes dynamics of how galaxies move. It changes how they would be expected to evolve, how those processes, stellar evolution, will play out on the largest scales, which then feeds into cosmological models of how galaxies move and evolve. So,
well, and presumably also, like, if we don't understand how the Jupiter-sized ones are really being formed, that would have a flow-on effect to all the other planetary type things like us.
Yeah, well, yeah, planet formation
we don't get
in general,
that one, then it's like it's all the planets, right? So, yeah.
So it's very interesting that you can go from something we just don't understand how these particular, maybe quite, in the grand scheme of things, rare planet-like objects, or whatever you want to call them.
Planets.
I'm over names
planets.
now. Yeah, planets are formed. How that can very easily, just in a few steps of logic, dictate the evolution of the universe. So this is a wonderful thing. It's all connected.
It's these dominoes of astronomical understanding that you just touch this one, and it's not that the whole lot goes down, but it does knock over a few other dominoes along the way, which is pretty cool. It's very exciting.
Yeah, no, it is. So I think, this is important on those larger scales as much as it is on the smaller scales. So I was just thinking about this kind of research where, so you have a prediction that there will be close to no examples of these types of objects in the Orion Nebula, for example, in this case. So when you set up a project to then go looking for them, I think this is actually the right way around to do things from a personal point of view.
It's very optimistic.
It is. But
we don't expect to find much, but we're going to look.
Yeah. So I think you kind of win both ways, right? Because if you don't find anything, you're like, yeah, well, that turns out that theory was right. And you can sort of think, oh, yeah, that's quite good.
Well done, us.
We understand.
I mean, to be clear, they went looking for stuff, like to have a really good look at something that they already knew was there, right? We'd already found a few of these, but let's just check that out to make sure that we were right. Yeah?
Yeah.
Great. Good.
And it turns out there was all these other ones, and they're now breaking some of our models and things, and we're a bit confused. And that's cool as well, right?
Yeah.
So
it's a win-win.
Your two outcomes are just, well, that's cool, or, well, that's nice. So you win-win, yeah. Whereas you take the flip side of that and you go looking for something that you expect to exist and it's not there, you're kind of annoyed. Or it is there. Maybe you're just like, oh, okay, well, that was there. I don't know. Maybe it's just...
We sometimes draw parallels and analogies between astronomy and cosmology and particle physics. This comes up. And strikes me that second one is currently where particle physics is, because we've got these honking great particle accelerators really hoping they dig up something, that they see something. And it's just not turning up. And that doesn't mean that the field is dead, not by a long shot, just that it's a really frustrating place to be right now, because there's a lot of physicists out there going, just give me something. Show me where to look, anywhere. And they just keep having these sort of negative results.
So maybe it's a glass half full, glass half empty approach, but I think I'd take that on board with my own research and say, I'm going to look for things that we don't expect to be there, because then I won't be disappointed.
That sounds like a good philosophy.
Yeah.
I like it.
Go find the things you don't think you're going to find, and then you're going to be happy either way.
It's a win-win.
Yeah.
All right, finding our way out of this particular episode. Emily, going back to this Guardian article where all of this started from, there's a couple of lovely bits of science communication in here, actually speaking with one of the scientists, Macorian, I think is how we pronounce it. Obviously had a chat with the journalist, and we spent a lot of this episode saying, is it a planet? Is it not a planet? I don't know. And he has a lovely approach to this, which is, the quote is, most of us don't have time to get wrapped up in this debate about what is a planet and what isn't a planet. It's like my cat is a Chihuahua mass pet, but it's not a Chihuahua, it's a cat. It's like, I don't care. But that's such a really good analogy. I love it. The other thing he said, which I thought was fantastic, was we were looking for these very small objects, and we find them. We find them down as small as 1 Jupiter mass, even half a Jupiter mass, floating freely, not attached to a star. Physics says you can't even make objects that small. We wanted to see, can we break physics? And I think we have, which is good. Like, I love it. Just the whole attitude of, yeah, hell yeah, let's go break some physics. And by the way, it's not a Chihuahua, it's a cat. Anyway, this is a fun episode. I like it. I'm glad we turned this one up.
Yeah.
So, listen, if people wanted to get in touch with us and, I don't know, for example, tell us about something that they're interested in that we might want to base a future episode on, brackets, tune in next week to find out what we're going to be talking about, because we've had a listener write into us with a really good idea. How can people get in touch with us, Emily? Is there a way?
There is, unfortunately, really good way that you can get in touch with us, and that would be, first of all, to go and peruse around the syzygy.fm website.
That is correct.
Because there's a contact form on there. You go on your computer and you fill in the details, and then we get the other end.
How did that go? Is that how you type? Do you make that sound?
Yeah.
Nice. Good one. Yeah, that is exactly what happened this week. We had a come through from a listener. And so tune in next time, because we're going to be taking a deep dive into, well, that topic of choice. Shall we reveal what that is?
No. Okay.
You're going to have to tune in then. But there are other ways that you can connect with us. We are out there on some of the social media. We're on the Instagram. Mm-hmm. What nommed
Syzygy
Insta?
Pod, SYZYGYPOD.
That's right. Or you can go to Facebook and just put into the Facebook search thing. This is how Facebook works. Just Syzygy Podcast. You'll find us. You will find us. We're also on YouTube. If you like to do your podcast by watching them as you listen, then we're on YouTube as well. You can go and listen to us on the YouTubes.
Do you get the nice pictures that we've been talking about in the episode?
No, but I'm trying to think of a way to do that. Currently, it's just a static image with a like as you often see with podcasts on YouTube, with the sort of the voice thing,
the
wiggling up and down. But I'm trying to figure out, is there a way that I could relatively easily, without devoting too much time to it? If you wanted to support the show, a number of ways that you can do that. The bestest way is to just tell everyone you know, so that they know that there is this thing called Syzygy, and they can go and tune in and learn all sorts of really cool things like JUMBOs, planets floating out there in space. That's the best way. But another way that you can support us is by going to patreon.com/syzygypod, where you can throw a couple of dollars our way a month to help us keep the electrons flowing through the site. And I went and visited Patreon for the first time in ages the other day. I'm a really, really bad social media content creator. You're supposed to do this all the time, and I didn't for a really long time. Went and checked. We've had a couple of new people come on board.
Thank you.
Welcome. And we put all the names of everyone who has ever supported us and continues to support us on the website at the great cosmic wall of thanks. So thank you to everyone who continues to support us. You're fabulous people. Listen, we should probably wrap that up there. So we will see you, give or take, a weekish time. Until then, Emily, it's been fun. Catch
See you
later.
later.
Bye, everybody.